Technology presents educational satellite television programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the definition and general properties of bases. In our last lesson, we discussed some common as well as indirect uses of hydrochloric acid, nitric acid, and sulfuric acid. Today, we will define bases in terms of the concepts of Arrhenius, Bronsted, Lowry, and Lewis. We will discuss the general properties of bases, and we will look at some specific examples. Students, if you are ready, we will begin. Bases exist in the same class of inorganic compounds as most oxides and hydroxides of metals. Bases are important in our daily lives in both direct and indirect ways. For example, sodium hydroxide is used to produce soap, paper, textiles, and many other items we often use. Potassium hydroxide is used to manufacture soft soaps and fertilizers. Bases are also very important within the chemical industry. For example, calcium hydroxide is used to produce mortar and bleaching powder. It is also used in agriculture to remove soil and acidity. Different chemists have provided us with several different definitions of bases. Let us begin by discussing Svante Arrhenius's concept. He stated that a base is any substance that ionizes or dissociates in aqueous solution to release hydroxide ions. Arrhenius bases are mostly metal hydroxides. Some examples include lithium hydroxide, sodium hydroxide, potassium hydroxide, and barium hydroxide. The following equations show the dissociation of a couple of Arrhenius bases. Sodium hydroxide dissociates to form sodium plus and hydroxide ions. Barium hydroxide dissociates to form barium 2 plus and hydroxide ions. Johann Nicholas Bronsted, a Danish chemist, and Thomas Martin Lowry, an English chemist, also simultaneously developed a definition for bases. They stated that a base is a substance that is capable of accepting protons. According to this concept, a base is a proton acceptor. Students, it is important to note that all Bronsted-Lowry bases are not Arrhenius bases, but All Arrhenius bases contain a Bronsted-Lowry base, which is the hydroxide ion. This is because hydroxide ions are capable of accepting protons to form water. Within the Bronsted-Lowry concept, an acid-base reaction is the transfer of a proton from an acid to a base. The following equations provide examples of this. Students, let us do an activity. Please explain why all Bronsted-Lowry bases are not Arrhenius bases. You may begin.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. Were you able to recall why all Bronsted-Lowry bases are not Arrhenius bases? All Bronsted-Lowry bases are not Arrhenius bases because Bronsted-Lowry bases include all substances that can accept protons, even if they do not release hydroxide ions in aqueous solutions. If you answered that correctly, great work. Gilbert Newton Lewis produced a more general definition of bases. He stated that a base is a substance that is capable of donating a pair of electrons. Thus, bases are electron pair donors. Therefore, the Bronsted-Lowry bases are also Lewis bases because in order for them to accept a proton, they should have a lone pair. However, Lewis's acid-base reactions include reactions that do not involve protons. These bases are able to form a coordinate covalent bond by sharing their lone pair with other substances. This acid-base reaction shows Lewis's concept. Let us move on with the lesson and discuss the general properties of bases. Bases that are able to dissolve in water are also referred to as alkalis. For example, sodium hydroxide, barium hydroxide, and potassium hydroxide are all readily soluble in water. Magnesium hydroxide is an example of a base that is only slightly soluble. Bases have a bitter taste. They also tend to be slippery to the touch when they are in dilute aqueous solutions. Students, it is important to remember that you should never taste or touch chemicals to determine if they are bases. Sodium hydroxide and potassium hydroxide, for example, are both bases that are corrosive and poisonous. Soluble bases change the color of indicators. For example, red litmus turns blue. Phenolphthalein turns pink. Methyl red turns yellow, and universal indicator turns blue. When soluble bases dissolve in aqueous solutions, they release a hydroxide ion. For example, the dissolution of potassium hydroxide produces a potassium plus and a hydroxide ion. When calcium hydroxide dissolves, calcium plus and hydroxide ions are formed. Bases neutralize acids, or acidic oxides, to form salt and water. For example, when sodium hydroxide reacts with sulfuric acid, sodium sulfate and water is produced. When potassium hydroxide and sulfur trioxide react, potassium sulfate and water are formed. When calcium hydroxide and hydrochloric acid react, calcium chloride and water are produced. One last property of bases is that they conduct electricity when they are in aqueous solutions. Solutions of strong bases are strong conductors, and solutions of weak bases are weak conductors. Now that we have discussed a number of properties of bases, please list them. You may begin.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Let us review the general properties of bases together. Bases are bitter tasting. Bases are slippery to the touch in dilute aqueous solutions. Soluble bases alter the color of indicators. When soluble bases are in aqueous solutions, they release hydroxide ion. Bases neutralize acids or acidic oxides to form salt and water. And finally, soluble bases are electrolytes, which means that they conduct electricity. Today, we learned about bases in terms of the concepts of Arrhenius, Bronsted-Lowry, and Lewis. We also discussed some of the general properties of bases. This is all for our lesson today. Until next time, thank you, teacher. Thank you, students.